We're set up.
We're few today.
Sorry.
We're few today.
Yeah.
Compared to yesterday. No, people are still coming.
There's a few on, but maybe it's people having lunch too.
Yeah.
Well, we have few new people online. Which were not here yesterday. Yeah. Yeah, Stephen, Justin. That's good. Haven't seen him in a long time.
But I'm gonna see him again. This is
Are we muted?
Oh, I don't think so.
Okay, good.
No, I can hear you.
Okay, so we have to be quiet. Who we talk about?
Hey, Thomas.
Hey. Oh, Astrid. Oh, Astrid. Hey. Haven't also seen you in a long time.
Yeah, same here. Sorry, I don't have my camera on my.
Oh, that's fine.
But
That's
yeah.
okay.
There's a volume control here if
Oh, that's good.
it's too quiet or anything.
Yeah. Well, that's good.
Everything's set up
Yeah,
technology wise.
I think Valeria is making sure the other rooms are ready to go.
Yeah.
So we'll probably start here in a couple of minutes. Then
If you join the Zoom call, just mute everything.
yeah, exactly. There you
I'm not the blessed, so
So I have internet. If you need me to share something,
yes.
that's perfect. Yeah, let me actually call in.
Can someone remind me of the passcode? It's Lisa. Is
Oh. Good question.
It's late.
you can go to the website.
Lisa asked.
Is there? Yes, and go to where it says you are an online participant. And scroll down and there's a click somewhere and then.
Java.
Oh, yeah.
Yeah.
Lisa asked WG.
Yeah, it's there too. Thank you.
There you go. Want me to share that?
Yeah, just to have some structure.
Mm.
So we actually have no specific, agenda or anything. So it's we thought that it would be good to start as we did for the white paper chapters. We just brainstorm the ideas. So in this Google Doc, I just copied the description, same as yesterday. The link to the sign up form, the references, and whatever I had so far. And we just keep it to sort of for the minutes, and maybe if any references or links or anything else come up, we can record everything here. And now the floor is yours.
Maybe for.
So- Oh, go ahead, Thomas.
Oh, go ahead. Go ahead. Go ahead. Tim.
No, I was gonna say, the gist of what we're what we've imagined doing is here in the description. There's a little bit of baseline work that certainly in my head needs to be done, largely centered around knowing what's out there and what do we want to look at that's being compared. So at some level, there needs to be, and someone may have this or have already done, I just don't know where, but an enumeration of the known codes that we might want to use for this project, whether or not they're in the public domain and whether or not they're maintained is probably the important thing. But then related to that, which isn't in this description, is that it would be good to know the provenance of the galaxies that are currently being used. So things like the LDC galaxy and what parameters went into it. And I know Valeria and I, for instance, have talked about this a little bit, but that's the sort of thing that we would also need to do, because it's one thing to intercompare the codes, but it's going to be another thing to kind of understand how anything we generate can be compared to the literature. So I think that kind of provenance of the existing galaxies, Heiss's the NYPZ galaxy, all of those probably would be useful to understand as well. So in terms of kind of making lists of things to do, those are high on my list.
Can I ask a question first? Maybe just take a step back. So what's the goal of this exercise? Is it to understand the caveats of the codes? Is it to understand what physics we are missing? So what's the goal of this? I guess like a much more basic question than you started.
Well, I think it's all of those things, right? I mean, at some level, right? I mean, I think what Tazo said yesterday, I think sticks in my mind as being really important, which is, we should define the assumptions we want to make and then see what we get from each of the codes to see if they're the same or not, right? At zeroth order, that's where I think it's good to start. So,
okay. Yeah.
So I think that it's a bit similar to this project 3 of the pre-Lisa EM business, right? And so I think to me, at least, the top priority is to get a better feel of the uncertainties in the really expected populations for Lisa. And then I think that, you know, another result and also a worthwhile effort, or interesting at least, let's put it that way, is to get a better feel of the differences between the codes. Just for, you know, generic reasons. Why
But-
people have done certain things and why others have chosen other things, where, you know, we can have a discussion on the importance of these things and also the impact of these things.
But Heist, do you think we can understand the Lisa uncertainties without understanding the differences between the codes? Because if they're giving different answers for the Lisa catalog, then we don't know if it's the codes, if it's true uncertainty, right? I think those two are intertwined in a difficult way.
No, I think that's right. But on the other hand, I think the experience from the popcorn work and other similar works is that if you really want to understand differences between different codes, that can be quite complicated.
Sure,
And,
sure.
and so one of the things is that if with sort of, you know, I think in terms of the galaxy, you know, what people assume for sort of global normalization type work, in terms of how many things that are born at certain times and how far away they are. If people can do an estimate or a rescaling or a calculation, whatever, relatively easily, in a way that if that's done in the same way, I think one of the very interesting questions is whether the differences that are in the published works are mainly due to different binary assumptions, mainly due to different galaxies, or sort of equally split over the two. And so I
Right.
think these are relatively low threshold things you can do without, you know, having to look in lots of detail at all the codes. And I think based on that outcome, and I would, it's a bit difficult to predict, but I would not be very surprised if the galaxy actually turns out to be a very important part. And the binary evolution turns out to be also important, but at a lower level. And I think that information alone is already interesting for the Lisa people.
Mhm.
And then the second step, of course, is then a much more hard question. What type of normalization / galaxy is most realistic? And, you know, those uncertainties in the population synthesis, how do they relate to what the real universe may look like? And one of the very frustrating things, of course, we can find that the codes give very similar results, but they're all wrong.
Right.
I think that's perfectly reasonable outcome, because there's many things that people have put in because somebody else put them in. Yeah, right?
Yeah, well, I mean, the only way to determine what's right will be to have Lisa data, right? So I maybe the
Well-
kind of alternative extension there is to imagine, you know, if we are getting different predictions, or if we do get similar results, how do you use that in concert with data then to make a decision about what the parameters the galaxy should have had would be, right? So that's not this project, but that's the natural extension of this past this.
But this is actually, I think we can do this earlier than Lisa data, right? There are not a ton of stuff out there, but we have now a reasonably well understood AMCVN space density. The Elm space density is pretty well known. So there are some anchor points, right, which you can try to reproduce. Whether that's then an extension gives you a good Lisa prediction, I don't know, but I think you can do stuff more. But that's then, of course, that's the next step to me, right? That's beyond like code comparison. That's like trying to understand the physics and make sure that it matches the few observations we have.
So
Well, we will have to decide on parameters though, right? So external inputs, whether they come from, you know,
Yeah.
observations or, you know, galaxy fire simulations or
Yeah.
something, right? We will
Yeah.
have to do that, so. But you just yesterday said that you couldn't tell us space densities.
Well, we can space, well, at a limited scale, right? The aim, I think, I would now argue like things like the AMCV and the Carter prediction, the Carter numbers are pretty similar to what Jan finds. And so I think we are getting at least a rough estimate. So, I mean, obviously it's not perfect, but it's better than
But
what we had.
you could give us a space density with error bars, which would be suitable for doing the kind of study we're talking about. Because then we can
Right.
just do the study at both ends of the error bars, right?
Yeah.
And that
Yeah,
gives you the
that's-
sense certainty. Yeah, okay.
Yeah.
No, I agree with Thomas that we will have, oh, sorry.
No,
Was
go
I
ahead.
talk- Yeah. Somebody needs that somebody decide how to organize the room versus the Zoom, I think, but we'll find that out. I agree with Thomas that there will be, we will know earlier. The other thing I wanted to say, which I think at some point could be useful here, is that a little bit what I've listened to some of the recordings from yesterday where I couldn't be there. I think here we can start writing down small projects that basically 1 or 2 people can volunteer to do. And so a number that come to mind is simply collect the papers that have said something about this and figuring out how many of something, you know, trying to get the information together about these papers. We did this in the white paper in a, well, I hope I don't offend anybody, but I think we did it in a relatively rough way.
Haphazard way.
Yeah, sort of, you know, roughly this number, and I think we can collect, because it's only, I don't know. I would say probably less than 10 papers, certainly less than 20, that really make predictions from population synthesis codes about the number of LISA galactic binaries. And so we can collect these and maybe see, you know, collect all the information about the prediction for LISA, but also about how to deal with the with the galaxy, and maybe even start making a list of you know, initial binary parameter assumptions, which probably are all the same, but anyway, it might be good to. I think we can come up with a number of small tasks that we can really start doing, maybe even already over the summer if there really are volunteers.
So Tassos wanted to make a comment.
I will make a different one now, though, since
Okay.
the conversation continues. If you include the binary W,
We can't hear you, Tazos.
I'm sorry, I will move closer. If you include in the LISA binary double neutron stars, then the bibliography is quite a bit bigger
That's correct.
than the 10, 15, 20 papers that you mentioned.
Yeah.
So
I think that's correct.
maybe a 0 step would be to decide which are the populations that we're going to target.
Yeah, to be honest, I think it's the big ones, right? We're really interested whether it's 26 million white dwarfs or maybe 50 or 5 million. And whether it's 100 double neutron stars or 10 or 500, you know, that's great if it would be a large number, but it's not going to make any difference for the foreground or for the massive black holes. And to be honest, Tassos, I think that you're right that there are many papers about double neutron stars and things like that. But I think most of these, correct me if I'm wrong, are of the type getting birth rates. So basically translating a star formation rate into a formation rate.
There's
rather
another
than-
class of papers about double pulsars, so these are more relevant to this.
Yeah. No, that's correct. And of course, there are a number that are actually include the galaxy and all this business.
Yeah.
That's, I guess, what you're referring to, right?
Yeah.
Yeah. Well, I think actually the number is still, you know, doable, I
Mhm.
would say. And it might actually be interesting to compare, for instance, the galaxy that are in the pulsar population synthesis with galaxies that we have used in white dwarf LISA. I'm not sure how comparable these two are. Well, they should be somewhat, but even though I've done both of these type of calculations, I can't really remember. what the
Are you
goals
talking about looking at historical results, Heist, or are you talking about
Yeah, yeah.
running new sims? Oh, okay.
No, no, so I think the first step we can do is look at the literature and try to collect.
Right.
And then I think the other part, so that's one part. The other part is that if we have, I talked to Valeria briefly last week, you know, there is a number of population synthesis codes in the world, and I think we should have one or two ambassadors who go around and see if they can essentially interest at least a number of groups to take part in this.
Well, and some of the
exercise.
groups are already right here, right?
Some of the groups are here, right?
It's so-
But Heist, implicitly, you set a priority.
No, so
You
I think
said-
I think the point
You
that
said-
Thomas, oh, sorry.
Yeah, I said that implicitly you set a priority. You said that the important thing that we need to understand here is the population of double white dwarfs, but because this is what is important for the broader LISA community, because it will form the foreground.
Yes.
We all agree that this should be the priority of our first project because it limits it, but perhaps makes it easier to move forward. If it is clear to you and to the rest of the chairs that this is what we want to do, maybe we can focus on that.
Well, if we think of, I agree with that, Tazos and Heist both. I think this is right. And I think if we keep in the back of our minds the priorities of what's going to be valuable to the consortium in the next year, that's exactly the thing we should be doing, because that's the thing that will influence all the machinations that go into the work on the Red Book.
Okay, I wasn't quite sure about this. Is the goal of this work really to get ready for to have an input for the adoption, or is the goal for us to do astrophysics? Because
Well,
if it's
a month ago, it
then-
was astrophysics, but in the last week, it's become a little more muddied.
because
Well,
if
I'm not
it's
sure.
astrophysics, I'd put the PNSs and even BBH and other type of stuff on the equal footing.
Yeah.
If it's getting us to the adoption, then I would only go with white dwarfs. I completely agree.
To be honest, I don't think that there will be a very tight connection between this work and the Red Book, for the simple reason that the timescales don't really match. And so,
Well,
I-
I think if you have a statement of the uncertainty, right, that will be valuable but I agree, we may not be able to produce a result they can use, right? Yeah.
no.
Yeah.
But I think I think the even if it's not the Red Book, I think an important motivation of this project, apart from the fact that it's very interesting, is that I think the LISA community is very interested in getting a better handle on the uncertainty of the foreground. And so I think that's independent of the Red Book. And that's why I think at least part of this project should maybe focus on the white dwarfs, or at least the systems that are numerous. Yeah, but I agree. I think people that know me will not be surprised to hear that the problem with neutron stars and black holes is I think that life becomes really very uncertain, and so it becomes an enormous challenge to get anywhere. But that's not a particularly good reason not to try.
Well, I mean,
Regarding-
as much as the codes can generate those populations, maybe starting with the white dwarfs just to give us broad experience with multiple codes and comparisons is the right place to start before you do something that's more uncertain like that.
Regarding the foreground, is it right to say that's really only the white dwarfs dominant, like the white dwarfs really shape the foreground? There's no like CVs, white dwarf M dwarfs, they're so low number that they really would not have any significant measurable effect on the foreground. Is that a true statement or not?
But they're lower frequency. And so you're
Yeah,
greatly
exactly.
helped by the
That's right.
fact that the sensitivity is going down there going down there
Yeah.
anyway.
Okay,
But it's really this period range between a few minutes and, well, maybe
Yeah.
20 or so, or 30. That's very relevant for anything that could stick above the noise.
okay, yeah. So
Yeah.
that's
And
yeah,
so
that's what I mean.
AMCVNs may be important if they are really concentrated, if there are lots of them, which we don't think based on the observations.
Yeah.
And the ELM ones are a bit funny too, but the point is that the observational space density is even lower than in our models. It's already very low in our models, but the observational
Yeah.
space density is insanely small if you talk
Yeah.
from the LISA perspective.
Yeah, okay. Okay, that's good. It makes it easier.
So I
can
think-
add to- Sorry, I can add to that, for instance, if IMCVNs are concentrated around a few 2-3 millihertz somehow, then they may change the knee of the background.
That is what,
It is like 30-20
okay,
minutes.
good. That's what I speak. I don't speak frequency.
So they won't change, right? Because they are fewer, they won't change the level below 1 millihertz. But if somehow they are somehow numerous or equally numerous as double white dwarfs at 2-3 millihertz, which is 20-30 minutes, maybe then they start shaping it a bit differently.
So that's something we don't know, right? We have an overall space density estimate from the AMCVNs, but we don't know if we look at particular periods, if there's a physical process, which I don't know, makes them lose contact or whatever before actually they reach 70 minutes. That I don't know that could, I don't think so, but that could influence the spacing.
So I think, sorry to push through a bit, but so I think that I see this sort of literature as a good project, and we should talk about this and see if we have people interested. The other thing I realized is we should maybe we can start here asking the question, how many population synthesis codes do we have that we can actually run? And so it's either because they're our own codes or because they're public. And we can always ask the people that develop these codes to help, but yeah.
So
Does that include the manpower to do the job?
Well, but I think isn't there, sorry, maybe I'm running too fast, but I think the aim of this discussion is to make a skeleton of the project we want to do.
Okay.
And then we can discuss whether we actually have enough people that are interested.
Okay.
And so the surprising thing to me in the pre-LISA EM discussion, where we had only, I don't know, 20 people online or so a couple of weeks ago, it seemed people were quite keen to actually start working. And so I think,
Yeah.
I imagine it might be the same here, and we should try that next week. You know, interested people can actually start doing something.
Yeah, I think that in the pre-LISA EM discussion, it was very motivating to start working because we start with we want to write these 3 papers or 4 papers.
Yeah.
And that was that is a good driver too. And here we are still like a bit more finding the common ground.
So where are we going to collect data here? Do we have a Google Doc? We're going to put all the notes, and so if we start listing off
Yeah.
names,
So that's
codes
the-
right now, where are we
Yeah.
going to put it?
When
Yeah.
I share, I
Yeah, you
can
can
put the.
So we can share this and we can keep it as a
Anyone?
so Heis is already.
Oh, I see. Heis and I are on that already, so maybe we should just go grab it.
I just put it in the chat.
Oh, okay, thanks, Thomas. That's helpful. Yeah.
I hosted it on the Astro Working Group Google.
No, that's perfect, Larry. Yeah, okay. Okay, so shall we keep everything here?
Yeah, I think it's a good plan.
So I can volunteer to try to find observational boundary conditions. It's probably for a later step, but it might be good to also collect them somewhere. Like space densities and the binary fraction we know pretty well now from Namas and Valeria's work, more or less. Good.
I mean, from Namas, but it is. And I think we also need to find, regardless of what populations or codes do we use, we need to find a common ground on how to run Lisa data analysis, right? And that should be the same for all of these projects. And yeah.
Sorry, I was distracted.
Do we
because
want to put some
all the
names
typing?
next
What
to
did you
these?
say, Valeria?
That like for all this project, possible populations or anything we come up with astrophysically, we need to find a way to run the Lisa data analysis that is the same for everybody.
Yes.
And for the codes, do we only care about binary codes or triple code as well? Because triples could make Lisa sources too, and
Yeah.
which are going to be non-negligible, by the way.
Yeah, so I think let's try to include the triples because it's part of the main question, right? What's the overall?
And even if like Lisa will see them, right? Lisa will see the gravitational wave signal and then well, that's actually hard to do. If we somehow identify the binary and we see an astrometric solution in Gaia, but that's actually very hard. Sorry, I was just thinking.
Well, yeah, I mean, those sorts of things are things we should just note down and think about when we have time, right?
Yeah.
So.
No, exactly. I was just talking while I was thinking. I should sometimes just think.
Yes, but if you don't write it down a year from now, we'll be like, what was Thomas saying when he was thinking? Tassos can't even remember what he said yesterday.
Very wise things. Does anybody from here has access to Star Trek?
No, but I think Ashley is interested in this
Okay.
project, or at least in project number 3 of the pre-Lisa, which I think is really.
I missed that. Who are we asking about?
Star Trek.
Oh, Star Trek.
Ashley Router. She's in a inconvenient time zone for many of the discussions,
Yeah,
of course.
right.
So
Has someone reached out to her about this already, though?
She signed up for the meeting, right? And she said she's in Europe during that time, but I think that was it, right?
Yes.
Okay.
Yeah, probably it didn't work.
Yeah.
So I don't know all of the codes that are, well, I recognize most of the names, but many of the names of the codes I'm seeing here are names I recognize from people who work essentially on binaries, black hole binaries detected with LIGO Virgo. I mean, obviously these codes can probably produce white dwarfs equally well, but I'm pretty sure some of them have, I don't know if they have actually, been checked or targeted with all the physics that is needed at lower mass. I'm So I don't know what to do about these.
Yeah, it might be worthwhile ordering these in terms of the ones that have been used for Lisa.
We can do a table like a code matrix, if you like, with columns which show if they've been used, and then we can sort it later easily.
Yeah.
Yeah, I think that in Tom's Bug's paper about Lisa double neutron stars, he already has a good table with the different codes, and he already like ticks many things which are similar and different. Yeah,
Who was
think
that, Valeria? What paper?
Tom Bug. Tom Bug, I think it's last year.
Last year's?
Yeah, in it, the paper is based on Compass.
Let's see if I can find his.
Yeah, sorry, I have no laptop with me, so.
No, that's okay. I'm looking. I'll find it.
I can find it.
There are some codes here, 4 or 5 of them, that are basically all of them derivative or updates of BSC. So I would say that one of them is sufficient. I'm talking about cosmic BSC, MOBS, binary C. I don't know what MSC is.
Yeah.
MSC is the massive multiple stellar evolution is the Adrian Hammer's code on triples. I think it's connected to Maser and not only. Maybe we should also add links to the codes or something.
Yeah, we can do that.
So regarding the benchmark, I was in the discussion yesterday, it was brought up very, very briefly, I brought it up, but the post-common envelope white dwarf main sequence binary. These are very close to progenitors of double white dwarfs. And they probe directly a physical process that is very uncertain.
Yeah.
It has been for many years in the back of my mind that I would like to compare population series with this. Is there a reason not to do that? Because I haven't thought very seriously.
You mean produce a prediction, or
Is there a reason that this the samples that I have in my mind is a series of papers by Zorotovich?
oh, but
from
these are the
SPSS?
low mass companions. These are M dwarf companions which do not do anything for the next 20 giga years, whatever.
That's fine,
Right.
but if what you want to do is common envelope physics for mass ratios that are similar to what you would get for double white dwarfs, then this is very relevant because you can imagine that the other way around, for the second common envelope, the mass ratio is similar to that.
Yeah, that I don't know. I know it's the Rotovich, they have done good stuff on like predicting alpha stuff in London.
Yeah, but these are very naive approaches, I
Of
think.
course.
So Tassos, of course, you will not be surprised that we have actually looked at this with Sylvia in her thesis. And so we actually approached it from the other way around because we have quite good information even on the second common envelope, because in white dwarf systems, the great thing is that the white dwarf, because it used to be the core of a degenerate core of a giant, has actually pretty good information about the properties of that giant. And so we approach from a different angle, which is asking the question, is the outcome of a common envelope different if the low mass companion to, say, a 1.5 solar mass giant, if it's a white dwarf, or a much bigger M dwarf with the same mass? And there the answer was, well, it doesn't look like it. But so I think you have to be rather careful, because of course the mass ratio is quite similar, but the compactness of the object, and therefore things like accretion and all kind of things, could be quite different. And so it's not immediately obvious that, and so I think, to be honest, for a double white dwarf, well, anyway, let's not preempt the discussion. So I always thought that the first, common envelope or mass transfer, however you want to call this, old people know that I used to get into big fights with people about this first, whatever it's called, mainly semantics, I think. So I think that's a phase that's really very crucial for determining how many double white dwarfs you have. Because if in the first mass transfer you shrink the orbit a lot, then you have much less opportunity to grow, a reasonably massed white dwarf for the second, and you have a much higher chance of actually merging in the second common envelope.
So would it be then a very good project to go and look, not in a population synthesis kind of way, but more scanning the parameter space and saying the different codes with the slightly different approaches that they're taking in assessing mass transfer stability, what do they say under certain assumptions about the stability of the mass transfer and the final outcome? So you start then saying mass 1, mass 2 orbital period, what would be post first mass transfer episode?
Yeah. No, actually, I'm thinking now that, of course, there's Vicky Calogera's work from the 90s on double neutron stars, I think, where she did sort of a analytic, where you start with the distributions and then you transform these distributions through mass transfer. You could do something similar to that. I think you're right that for the lower mass systems, because you don't have the kicks and you don't have all the complications there, you may be able to write the relevant steps in a sort of toy model thing and learn something from that.
No, I was not talking about the toy model. I was talking more about comparing let's pick two codes, BSC and MESA. What BSC and what MESA says that the post first mass transfer orbital separation will be, given an initial set of parameters, which means stable, unstable, and what will be the final separation.
Yeah, because this is partly done in this popcorn thing, right?
Popcorn didn't analyze MESA, did it?
No, I didn't have
Not
MESA. I didn't have any detailed codes, but yeah. But I think you could. So if I look at this list of papers, list of codes, I think it might be too long. In the sense that it's going to be a nightmare to do the bookkeeping if we use all these codes.
Right, but we should use the ones which have been used for Lisa. Have all of these been used for Lisa?
No.
Definitely not.
But it depends a bit on what you want, right? I mean, I think as Astrid said, we do this partially because it's interesting to learn what the different codes are doing, because we may actually stumble upon things that either we need to focus on figuring out,
Sure.
or we could just learn from each other. Anyway, I think we won't have the manpower and we won't have the people on board to do all the codes, so we can just focus on the ones where we know much about.
But then, for example, for triples, right? So I mean, if they contribute significant to the background, then somebody has to check it, right?
Yes, no, so I think, but I'm not, you know better than me. Are there different triple codes? Yes, I guess, right?
Definitely, yeah. So there's at least several. So I mean, Sylvia Stress and Adrian Hammer's MSc, and then there's another set of people working in the Cosmic group, I think, exploring the effects of triples.
Yeah. So I think we should, my approach would be that we say, for triples, the most important question is, you know, how important will they be? In the sense of how different will a galaxy look like for Lisa with triples and without triples?
Mhm.
And so I think that's a question that maybe
It's
I'm
almost
not-
a separate project.
Yeah, I'm not. Yeah, I think it's separate. And to be honest, I don't think anybody ever looked like. Or have I missed papers?
I've never seen a population study done. Yeah.
No, not yet. There's very few population studies with triples, and they have been mostly on first phase of mass transfer. No, there was actually a study which was trying to make tap on A sources from triples. That was with Sylvia as well.
Yeah.
So they must have subpopulation of these sources.
I thought the problem with the triples that they don't know how to model mass transfer because it's quite non-eccentric.
Yeah, this it's not fully complete as well, the physics.
So Tassos, can you write in the document at some point so you said you want to compare basically single steps, right? Is that what you were saying? Rather than the end product.
Yes.
Okay.
If our goal is to understand where the differences are coming from, I guess this is.
In a way, it will be done because that determines the channels that binaries go through. So I guess it will be anyway the part of the work. Mm. And also a question, if we do the step by step, then comparison, do we have solid EM constraints on white dwarf main sequence, for instance, or, you know, the first stages?
I don't think so, because in those systems, the white dwarf is hidden behind the main sequence star. And so it's very hard to find them, identify them without, knowing the selection effect. The thing what might be easier is the main sequence stars, progenitor systems, like the very first input step. But that doesn't really help because you want to have a benchmark after the first phase of mass transfer. I think it's
You mean mass transfer? Just
after so basically the main sequence white dwarf systems after the first phase of mass transfer, which have what periods do they typically have? Like days, months,
Hundreds of days,
days? Okay.
not much longer. They're a very long period, typically. Well, at least we think. If you calculate backwards from the observed double white dwarfs
Yeah.
that now have periods below a day, then the
Yeah.
radius of the last formed white dwarf is basically more than 100 solar radii.
So that means the period, the orbital period was months.
Months at least, yes.
So I don't know that, but that might be something we can do with astrometric solution in Gaia.
That's what I was thinking too, right? They even thought they had found these black hole
Yeah, exactly.
systems,
So
which turned out to be not true, but anyway.
That's
yeah.
exactly. So that's the way to do that. I mean, that's actually a quite interesting project where you look for astrometric solution. Main sequence does with a dark companion, and from the astromet.
Yeah, but do you know the dark companion? Like,
Good question. I would have to sit down and think about this a bit. If you have the astrometric solution, you might get something. If you can, yeah. So if you have the astrometric solution and then you compare to stellar evolution models, what primary star you have, and what mass this star has, I think you can say something about the mass of the companion. I think so, yeah. And then if it's a dark companion and it's 0.6 and right, so and you can exclude an infrared excess and it's not a black hole or neutron star, I think you have a good solid way of saying it's a white dwarf. And if it's a young white dwarf, you see anyway UV excess. So that could be an interesting. Well, most people think finding black holes. That's not a big.
About why.
Oh, okay.
White binaries.
White binaries. Okay. Yeah. So that's something which could. I think that's an interesting exercise to do. Right. I mean, looking for astrometric solution is really easy in Gaia, and I mean, Ingrid could probably do this within like half an hour, and then try to find. Yeah, exactly. And then try to find the unseen, the dark companions, and then try to find. Yeah.
I think it's more complicated, Thomas, because we typically expect them to be 0.3, right? And so I think hiding a 0.3 main sequence is pretty easy.
Yeah.
So I think it's quite difficult to to distinguish. But you know, if you get number statistics, I would say that yeah, we could maybe do something with it. My impression was, but if indeed somebody knows more about this, my impression was that the periods would be sort of only partially wide enough to be picked up by the astrometric solution, and so you would miss an unknown fraction at say periods of 20 days or 30 days, which I think are yeah.
But they should still show an excess in an astrometric. They should show a high astrometric uncertainty somehow.
Yes.
And then if they show these nice lines in these calcium whatever lines, then you should see a radial velocity shift.
Yeah. No, maybe with the radial velocity of Gaia, because of course.
Exactly. Yeah, that's what I mean. Exactly.
So I think so. Okay. Anybody type this up, but it's maybe not for this particular. This is a code comparison.
Yeah,
discussion.
This is an interesting project, but it's definitely something where a student can easily spend a lot of time on it.
Yeah,
I think that's not something short term, but certainly something somebody should do.
Yeah.
Maybe I find a student. I don't know.
If you want to benchmark the population calculations against reality, then the hot subdwarfs, right? Stefan's sample might be pretty good. It's a specific subset of the initial conditions, but it's a good set to compare to the models.
So there actually the MESA calculations from Joris Voss do a very good job in reproducing the population of stable mass transfer system STBs. So there, I mean, we know MESA actually works really well.
Yeah, I should mention that that same study has a follow-up, which is reproducing the short period population of SDBs quite well as well. So not yet impressed though. But then it takes another step to get it to double wide dwarf systems, for example.
Yeah, it's a specific set of initial conditions. Yeah.
Well, there's also lots of post-AGB, post-RGB binaries, which are very similar orbital frequency, properties as the SDBs. Well, maybe not really, but anyway. So, and certainly they're also bright. More and more periods are determined. The problem there, of course, they're all eccentric. But that's
Well, SDBs are also eccentric, but not as eccentric as post-AGBs. And despite that, the periods are explained very well, but post-AGB periods are not explained as well for some reason.
No, I don't think we know all the. I don't think ordinary stable mass transfer easily gets you where you want to for all of these, but yeah.
Yeah, it's a mix of probably still, especially with giant branch pulsations and normal early AGB stars, and so it'd be harder to disentangle.
Right, so the surprising thing is some of them are actually post-RGB. And of course, in our galaxy, we don't know, but there's a lot of LMC or SMC, I always forget, one of these Magellanic Cloud things where they know, right? I mean, you can just see they're not bright enough to be post-AGB. So it's not something that is unique to AGBs, so we have to be a little bit careful in.
Well, SDBs are also past RGB,
right,
besides quite a voltage. So I mean, it's actually quite interesting to compare. I mean, maybe science value even.
So guys, there has been we had the SDB meeting last week, and so there was actually quite an interesting result if you talk about SDBs, and I don't know if they can work as a benchmark. So as an example, for post-common envelope SDB systems, we find that main sequence M-dwarf companions, there's none with periods above 33 hours. That's like, this is not a selection effect, this is an observation effect, because you would see them in tests easily at 2 or 3 days. And so there's a clear benchmark where you say there's no SDB low mass M-dwarf systems above 33 hours, or like, let's say a little more than a day. On the other hand, if you take white dwarf companions, SDB white dwarf companions, they are all over the place, up to several days, even tens of days. So I don't know, this is something where maybe the binary population could, like, right, as a benchmark.
Although for that, you probably want to use method because it depends on the amount of stripping. So if you have a bit of hydrogen left at 0.03 solar masses or something, it could turn your SDB into an SDA, for example, or into a horizontal branch star, although that's very rare though. I mean, it's actually quite entangled. I mean, so if you have white period, then you have less stripping, and so if you have less stripping, you could have more hydrogen on top, and then you could look differently from SDB, for example.
Yeah, but I think Thomas, this is more for Tassos actually, right? I think this is really quite directly probing common envelope.
That's right,
physics.
exactly. So that's probably then exactly. So that's more the next step if we are comfortable with all the codes and then really trying to make new and some like new numbers, then we can use these numbers as benchmark kind of. The codes have to be able to reproduce that population. I think that's for later stage. I know. I'm just saying the observations are getting better.
No, I think that's true, and so.
I mean, this is really part of the pre-LISA EM work, right? This is what's going to happen in the next decade. So we should keep all of this in mind. So
Sorry, my brain started working after Thomas said it, but the white dwarfs are more massive, right? The M's are all 0.15.
So there's actually, we have really good, this is something the SDB community has done a good job with tests and all these things. It seems to be that the like run-of-the-mill, like typically SDB, which came probably from a one solar mass star, these white dwarf companions are not, they're actually quite low mass. They're more like 0.4 to 0.45, 0.5-ish. And only the very compact systems, which came probably from higher mass progenitor systems, they have 0.8 solar mass white dwarfs.
No, but I mean, that you said that the SDB plus M, right? They are short period, while the SDB plus white dwarf are all over the place. But I think the
Exactly.
M's are all very low mass, like 0.15,
That's right. That's right.
which is
Yes,
not
that's-
like the white dwarfs, right?
That's exactly true. Yeah.
So I think
Yeah,
that
that's-
there's something funny happening, that there is this channel
Yeah.
of, say, a one solar mass plus a 0.15 that's
Yeah.
just about right, and then just there happen to be many of them, and they're all almost identical.
Yeah, exactly. That's true. Yes. So that's something, I mean, should be, I mean, we know what goes in more or less, we know what comes out. So that's something which eventually can be tested against.
So the question there is, where are the SDB plus 0.2 or 0.25 solar mass main sequence companions? Because you would expect them to survive the common envelope, be maybe similarly abundant. And so why don't we see these? And so that's maybe there is actually
Yeah,
a
we
mass
don't-
ratio difference.
So that's the thing, we don't have masses for most of the companions, but the masses what we have, they're all 0.15.
Yeah.
So I don't
Anyway,
know.
maybe
That's-
where this I should
Sorry,
go
yes.
to a SDB meeting if I'm so interested.
Yes, you
Sorry.
should. There's one next year in September in Armagh, so you should
Okay.
come.
Should we try to identify some more practical
Yeah,
things?
Sorry.
Yeah, maybe also how to run this, right? I mean, the point
Where
is
to store as well.
sorry.
What are we going to use to store this, to compare as well, goes to the practical stuff.
Yeah, and so I'm sort of wondering whether we should really do a really distributed project, right? Where we really spend a lot of time cutting up the work in small chunks and then assigning chunks to people, and then have some system where you can report or you can fill in the outcomes, because we're sort of, I think, too big to really work together, because I think we're easily, what is it, 10 plus people, or we find a few people who can take the lead, right? I mean, if there's a couple of students who want to say, yes, we want to do this, like Sylvia and the company did with the popcorn, then of course it's solved. But
Right, but in as much as there are people here who run some of these codes, then our groups are the obvious ones to run the codes. But I think what Valeria said is probably the critical thing, is it's one thing to run the codes, but then we have to figure out what we're going to compare so that all the data can be transformed into some format that we can actually assess, whether it's just by direct comparison, or we have to agree on what graphs we're going to make, or we're going to write some big inter-analysis code that takes binaries and derives Lisa catalogs. I mean, we should decide what that comparison will look like so that we can do it in some kind of common way. And that will be different work than actually generating populations from the codes. And if you're gonna compare results in the literature, that's a completely different kind of work, because then you don't even have to touch the codes. But you do have to understand what's in the literature. So
yeah, and so I think that's actually something we can start on, and maybe we should give ourselves a target date of, I don't know, early spring or early fall, that we're done with this literature business, right? Because it's really not a huge amount of work. And I think it will actually make a lot of things clear. For instance, whether the normalization that's used in the different codes, how different it actually is.
right. Yeah.
Where, you in principle only need to do an integral over the assumed star formation rate over 10 billion years, right? And that's something that surprised me in the past, that at that time when we looked at that, for instance, the Russian code assumed one solar mass star formation rate per year, and for simplicity constant, but that of course gives you only 10 to the 10 solar masses of star formation over the history of the galaxy, and the code I used had 10 times more or something.
Right. Yeah.
And so
yeah.
then if you then start comparing type 1a supernova rates, you might find rather large differences,
Absolutely, yeah.
which have nothing to do with the binaries, right? It's all normalization.
Yep.
Yeah, but for the, like, if we focus on comparing, not the reality, then having a simple constant star formation makes sense because it's, well, just easy for everybody. And it's, at the end, it's, right, it's sort of, whatever star formation is, you can always find a representative constant star formation that would yield you the same mass. Something like that. Like,
We could
I
also-
mean, it's, yeah, sorry, go ahead.
No, I'm sorry, keep going.
No, I didn't have like a fully formed thought, so.
I was actually thinking we could also remove the star formation process initially and just assume we have a single burst of star formation. We simulate, I don't know how many initial binaries, 10 million, and we look at the output at the time of the formation of the second white dwarf. Which period do we have and which masses do we have? It won't include anything that can happen beyond that, so no gravitational wave emission, any further interactions, but at least it's a clean thing that doesn't include any galaxy models, but it will allow us to compare binary codes.
Yeah, so if we have from the codes, right, the formation rates at certain stages, then yeah, adding star formation is an easy thing, and then that can be normalized by the mass of the galaxy, and that's sort of a very easy rough estimate of the final number.
Right, but this is for the second step when we're rerunning codes. Going back to the literature.
Yeah, yeah.
First goal, we really need to do this calibration, at least in a like in an order of magnitude way, and say when we're comparing paper A with paper B, these are the differences.
Yeah, but I think Astrid is right that many codes probably work in that way, right? They generate binaries where they then calculate for a certain amount of time what happens to them. And so it's probably actually the simplest way of comparing. So I actually like that idea. I know certainly in CIBA this is the way we do it. And then in order to then include star formation rate, whether it's constant or not constant, you have to resample from these results in some way, which is, you know, in principle not difficult, but so the thinking I had about the constant star formation rate is that it's a better representation of the galaxy than a starburst, but it's not very good either. So I'm not sure that better is, you know, less worse, whether it's worthwhile looking at this at all. But
well, we can do both. Once we have one, the other one is easy because we sort of all did that exercise already to do the constant.
Yeah, so we should swap the two, and yeah.
Yeah, I think we can make the choice in Cosmic. We can do both, so.
But I may add maybe that a step from a constant star formation rate to a realistic galactic history, for example, accounting that thick disk was formed in a burst and then thin disk was continuous, for example, and these things, I think it's very small. So it's very easy to get the canonical, typical accepted galactic model as well.
Yeah. Well, I think we have dreamed up work for a lot of time, so we're too efficient in making plans.
Yeah, so we should, right, well, we should agree what we're going to do over the rest of the summer, maybe, but we have a couple days. But from what's in the document here, we should decide which codes we're going to focus on, maybe. And then maybe the other thing we can do today that I would is do we have an assessment of what kind of workforce is available for this? I mean, there's those of us in the room, but I have 2 students who are working on work that's a trajectory through this. So, right, there's more workforce than just those of us who are on this call, and that'll determine what we can do and how long it'll take.
I think that Sylvia mentioned to me that she and the postdoc can do some work on the SIBA side. I mean, postdoc with the Sylvia's, I mean, team as a team.
Yeah, right. Yeah, so maybe putting names next to things would be helpful too. I don't know.
I see, if we leave the pre-LISA EM project number 3 apart a little bit, even though it's probably the same people, maybe we can just have people championing some parts. And so there's the literature study. I think there is the code comparison, and then I think maybe the thing on some experiments with this more detailed comparison, like what happens after the first mass transfer, what did you end up with? And in some way a link with the observations, but that's getting on the project 3 territory, but yeah, I think that's a good bridge. So I forgot who volunteered to take the lead on the project 3. Jan, didn't he? Jan van Roestel, I think.
Yeah, but he's observer, and then I think people mentioned Katie, but I think Katie didn't commit. So I don't know.
Katie Brevik?
Yeah.
Well, I think so, right?
But we could be the efforts here could be the theoretical part, right? So I think if he takes the the observations, and so there I think also there's a part on collecting what information is available, and I do think the Gaia link is very interesting. So maybe we can stimulate somebody who knows how to do this to have a good look at this in the relatively near future. I'm not looking at anybody particularly, of course.
Even if you do, we cannot tell.
But I hope somebody would feel
I feel some pressure, but I'm not sure if that's.
Well, what kind of are you specifically thinking, guys? Are you thinking about the white dwarf main sequence?
yes,
Okay.
the one we just talked about. I think it would actually be very interesting, but you would need to do a pretty. So one thing we could do to help this person, I think, which then ties very nicely with Tasso's idea, is make a prediction of the mass and period distribution of white dwarf main sequence binaries. And so of course Sylvia has a paper on this, but I think it's mostly about the low mass main sequence, but I'm not quite sure. We of course had the more massive ones, which we then had to brush away in terms of luminosity ratios, etc., to compare to the observations. But because it might actually be useful if you start looking at the Gaia data to have an idea of what kind of mass and period distribution you would expect.
I think Gaia astrometric binaries sometimes come with a mass ratio already, and that already gives us something, right?
Yeah.
So doing a quick search is relatively straightforward, and but doing that in a proper way with proper numbers, like real numbers in the end, that's probably harder.
Yeah, that's exactly what I was going to say. Yeah.
Sorry.
No worries. Yeah. What is the timeline for when that's needed? I mean, I can't officially volunteer because I'm not in the consortium officially. But
Well, you will be soon.
yeah, I hope so. Yeah.
It's no problem. I think we are open to anybody who's interested, but you know, frankly, I think this is very interesting for sort of Tassos type comparison, which I think is step 2 of the theoretical part. If we forget about the literature study for the moment. So I don't think this is going to be anytime soon, right? It's going to be 1 year, I would say.
In 1 year, I might not even have a job, but if I do, I can probably do it.
Well,
You should be more optimistic than that, Astrid.
we can maybe collectively think about solutions for that. I don't have any money at the moment, so don't misunderstand me, but yeah, it would be good to have people doing this. In the meantime, I have found Sylvia's paper.
So maybe the other part to direct initial effort is to, right, I mean, the goal with or the kind of notion we had started with the initial discussion of the large projects was that there would be a publishable result in the end. So in terms of kind of framing the work we start with, maybe defining what we think that look like might help guide us towards the right things to start with. I mean, what will a useful paper in the literature look like related to this project? That requires the big group as opposed to little small sub projects or individual student theses.
For the code comparison, the obvious thing I gather from the discussion is to see how the foreground varies based on different physics parameters, codes, and galactic model.
So that's a multi-dimensional parameter space to explore. But do we think that's too much for a single paper, or is that 2 separate papers?
No, it's I think it can be a single paper.
Okay.
Because basically,
Transformation is easy to change.
yes, and also the like recently with the together with the Nikos Karnesis and his student, we did variations on the galaxy. Use it okay, and we estimated the background in an iterative manner, so it's not fully realistic because it's still based on signal to noise, and it's not I mean, white words there you still don't know exactly which are properly resolvable in a multidimensional sense. And basically by varying whatever of the galaxy, the only parameter that mattered was the mass of the galaxy. However, there was also, well, there was a caveat to that. But if I pick the galaxy and I with only one binary population synthesis model and I change it, the geometry, the background varies mainly with the mass. So then we didn't go forward because then varying binary population parameters, it's a lot of work. So yeah, I mean, it's definitely a big group project, and
Right.
It requires yeah, many inputs from different expertise and codes. Yeah. But star formation is something that's still to be checked. Yeah.
Yeah, I think in my head, I was mapping star formation into all galaxy parameters. So metallicity, structure and components, that sort of stuff. But yeah, so.
And also, yeah, so we did some tests on star formation, and unless it's very different, let's say single burst versus constant star formation, there are no like big differences. So since the star formation of the Milky Way in the past several giga years is fairly constant, whatever model you use that has this corresponds to this fact would produce would not make any like visible difference on the foreground.
Right.
But if you pick a very, totally different star formation, for instance, you put a lot of star formation at recent times, of course, it will be different.
Do we have a sense for delay time distributions for laser sources? Like, is it 1 to 4 gigayears, or can it span longer to 10 gigayears?
Can you repeat the question?
So do we have the sense for the delay time distributions for laser sources? In other words, the time between the starburst and the, well, the different possible times at which the laser source is formed?
Yeah, I guess that comes from the, well, that definitely comes from the codes, right?
Yeah.
Then yes.
No, just a number. I mean, they do it a lot for type 1a supernovae, like all the time, like one scenario, one delay time distribution, another one, another. So they differentiate it that way. But I mean,
there you're talking about the delay time between the formation of the white dwarfs and the merger.
And exactly, yes, that's correct.
So,
Well, but they don't merge, right? At least as
Yeah.
sources.
That's the thing. It's a different concept.
Yeah.
It's a bit
Well,
different.
but I think says, I think the answer is we don't really know, right? So it could be that the double white dwarfs are typically formed 10 billion years ago, and they are now in the Lisa band. And it could also be that they have formed 1 billion years ago, and they're now in the Lisa band. I think for Lisa and for the binary evolution, that's not even a major difference. But of course, for the question, what was the galaxy like when they were formed? It's a major difference.
Yeah.
So I think we can take some information from the observed double white dwarfs that are short period, right? And we have a number of short period, and they're typically not very hot. But yeah, the point is that's talking about hundreds of millions of years, right? And so I would argue that I don't think that most of the Lisa sources will be significantly less than 1 billion year old. But whether it's 1 billion or 10 billion, I think it's quite difficult to say.
Yeah, but it should follow from populations.
Yeah, no, I mean, in the models, of course, we know, but in the of course, there's this weird, I always forget which way around, but maybe Thomas knows. The ELM, very short period ELM source, I think it's about to merge, but it's very cool. Or relatively cool. And so I think it's quite surprising that there's sort of this period of hundreds of millions of years in which we could have observed it at slightly longer period. And yet we observe it 1 million years before it will merge. which a priori is quite unlikely, but of course we only have a few. So
It's low number statistics.
Yeah.
That's just, could be just lucky. And the eclipse probability goes up as you go to shorter periods. So there's this kind of selection.
that's
in that
correct.
sense.
That's
But
correct.
I don't think anybody like calculated proper probabilities and everything. So that's still needs to be done.
I'm sure Tom
lucky
Marsh did, and he was quite surprised. But anyway, it's
That's right, yeah. Yeah. Sure.
Mhm.
So we need a coordinator for this big project. We were about to volunteer on something before. That's what
Like
you were about.
I'm sort of will be behind the scenes anyway, right? As a Astro working group chair.
Yeah, we
Okay.
think the chair should
Some of
not.
you.
I think that's
But
it's a perfect project for a postdoc who wants to get some experience and is a theorist. Pointing on, I think that would be a good coordinator. To me.
So theory.
Mhm.
Anybody present?
there was also an idea from the Astro working group chairs that there should be more than one coordinator,
Yeah,
right?
I think it
I
should
think
be
that's
two.
absolutely true, yeah.
Actually, for our chapter, if it was not 4 of us.
Oh, yeah.
Kind of like motivating each other,
That's
pushing
true.
each other, we never finish.
Well, do you prefer, because for the code comparison, it might sense it's really a theorist to know the code and everything, right? But if you then include the data, we have Jan who volunteered for project 3, who is actually on the call right now. I think he joined.
Mhm.
But yeah, for this code comparison, I think it would be good if it's theorists because they're closest to the source anyway. Sorry, 2 of them, yeah. Sorry, I'm speaking as I'm sorry.
No, but it's true.
Yeah.
2 or even 3, right?
Even 3. Yeah. A representative from each code. Kind of.
Yeah. So that can be like one of the first action items to look for volunteers.
Yeah, I think that makes a lot of sense. So maybe what we can do is certainly within the groups that are working on population synthesis codes that are here, that we take as a homework to have a discussion if there is somebody related to the different. So I and or Valeria, I guess, can talk to Sylvia about if there's anybody for SIBA. And I guess there is this famous postdoc that was mentioned. Seems an obvious person to
Yeah, I know that
volunteer.
Sylvia will be, yeah, Sylvia will join us tomorrow, so she will confirm personally.
Okay.
I don't want to put any names, but yeah, there is a candidate, yeah.
So on Cosmic, Katie is the obvious person. I don't know if she signed up on the Google form, but whether or not she wants to coordinate or not, certainly in my group will volunteer to do the Cosmic work, but I can't coordinate, so. And I don't have a postdoc running Cosmic, so I can't, I would rather not put a graduate student in a coordinator role. I think it's a little too much on their plate, so. Or at least the students at the stage they're at now in my group, so.
So in a discussion that I had with Heis, it came up that whoever is the coordinator or running the codes, this person should have some deeper understanding of the parameters, not just being able to run. This is just a comment, general, not target.
Well, each code's a labyrinth down inside the code, right? So the person who runs the code has to understand all of that at some level, right? I guess you could just run codes by pushing buttons, but
Yeah, so that
I'm imagining Siva and everything else is as finicky as Cosmic is, so.
Okay, so that's the first action item. It is still pending, and it's fine, I guess, for now.
Just to clarify something so that it is easier to approach volunteers. Do we imagine the coordinators having more, okay, the coordinating role, of course, but being more supervisors, younger researchers that will run the work to write the paper, or they lead? Because that requires different time commitment in the one or the other case. I don't know, more
Well-
senior postdoc like Katie maybe is more willing to supervise somebody versus.
Yeah, I mean, when we get to the paper writing stage, we could assemble a paper writing team. I don't think we have to decide that at the outset, do we?
No, but for sure, like the coordinators' names should be pretty high up on the list,
Sure.
right?
Sure.
If not, I mean, if not
But-
the highest up.
But I think agreeing to doing the coordination on the project now shouldn't mean you're agreeing to be the lead on writing the paper, right? Writing the paper is a separate task in the scope of the big entire project. So, you know, when we get to that task, we can develop a sub team who's going to you know, put the skeleton down and get everything in place.
Sounds good.
And when we did the white paper, it was just about writing the paper, so it was natural for the coordinators to do it. But yeah.
Yeah, I'm just imagining that if myself, I was a postdoc and I wanted to be involved in this, I would be interested to know whether I'm signing up to lead this work, meaning to be also a first author or second, whatever, affecting the leading team or not.
Well, especially for postdoc, it's important to have something because, right? I mean, that's how they survive.
No, but
I know,
if
that's
they know, they have a different commitment to the project, right? They're committing to supervise somebody. That's perhaps also a valuable experience for a postdoc. But it's a different commitment in the work that they're gonna do and the priority they're gonna set.
Yeah, no, I understand your question now, Tazos. Yeah, so.
Yeah, so this is what I was more explicit.
Yeah.
Like I would, I guess, I would put coordinators.
The leading author,
Yes.
leaders of the project.
Yeah, because I imagine they will do a lot of work, maybe running, maybe, you know, coordinating also the writing. Maybe they won't write directly, but they definitely would decide what is going to the paper, in which order, and things like that. So I think yeah, I mean, I would expect to be, yes.
Yeah, I agree. I just want to make it clear.
And what's the timeline again? So like the idea would be to have somewhat of a literature review and group ready by the end of the summer, and then sort of have it within a year time scale, conversion tested and run and written paper. Is that the plan?
I think that sounds right to me. It depends on how long it takes the codes to run.
Yes.
If you ask Sylvia, she might say that might be a very kind of tight. From her
No, I mean-
experience of-
In reality, yes.
yeah, that's a tough question.
The feedback I've heard from Sylvia about the popcorn code is that the popcorn paper, that actually it was quite a hell of an effort. So it's actually, I mean, but it partly was because, I don't know, she was heavily involved in that. So
But it's good to set goals and
I imagine that this will be a very high impact paper for
Yeah.
whoever write it, because that will be the prediction of the uncertainty of the
Exactly.
foreground stamped by the LISA Astro working group. So it will be very widely used for the next
Exactly.
10 years.
And then showing this coordinating experience for postdoc is something which I think is a very good experience in existence.
Yeah. Well, anyways, would anybody of the observers be interested in teaming up?
On this code comparison thing,
That's for
Yeah.
later stage observers, right?
Yeah.
We are not useful. At this point, we are not useful.
But at a
Yeah,
later
that-
point, it's
that
going to
would
be almost central.
Interesting to join the
Yeah, at a later point.
specific step plus specific observed step.
Exactly. At a later point, I think that, yeah, for sure.
Okay.
I mean, probably writing comments for sure.
Oh, yeah, that's for sure. Yeah, exactly.
Okay, let's give it a go then. So can volunteer for that.
There you go.
So, okay, that's good. So I don't have the. Maybe you can start an item on the Google Doc and start an item like coordinators. And yeah, just put your name and also like, like the code that you. So far, we talked about that representatives, right, should sort of coordinators should represent some codes maybe. So just next to your name, put also the code. Just at least for our reference.
So we are presenting Seba and Mesa.
Okay. Thank you. Then I guess we are reaching out to Katie because her name was mentioned, at least to know whether she's interested or whether she has somebody that she can volunteer for us.
I'll put I'll put my name and her name there for the moment, but I'll reach out to her.
Somebody from Compass? When Tom Wag comes to my mind, he's not
Yeah, Tom's been working on really great tools. He's connected. Yeah, so
Yeah, so they don't have quite words yet, but maybe they're thinking.
okay.
We're just wondering whether there is anybody from Compass community. And
Steven is here. Yeah,
yes.
Steven is here.
Steven's here, yeah, and waving at us.
Yeah. Can you recommend somebody, Steven?
Tom's great. I'll ask him on our Slack whether he wants to stay with this. So okay, I'll ask him.
But Tom is
And then
PhD.
there's the whole group of Ashley. So Ashley started using Compass as well. So Ashley's
Right,
great.
Ashley.
Yes, Ashley.
Ash Reuter is using Compass?
Yeah.
Oh, okay, cool.
At least to some extent now. Yeah.
Okay, I didn't know that, yeah.
Yeah, the only thing, Stephen, right? Tom is PhD, so it's a PhD student, so we have to be careful.
Yeah, there we have to
Yeah,
be careful.
so that it's not too much work and responsibility. I mean, yeah.
Yeah, no, I totally agree. He's more impressive than I ever was, but yeah, I agree.
They always are, aren't they?
And also if his supervisor is fine with this, right? Yeah. Mhm.
And we should ask Ashley if she has somebody.
So whoever has access to Google Doc next to.
That sounds like a good idea too. Yeah.
Also Ashley. And, and also.
Is
on
someone,
campus.
is someone gonna, did Ashley did volunteer? We need to reach out to them.
Oh, yeah, I think reach out.
Yeah.
Okay,
Both.
so
Question.
Stephen said he'd reach out to Tom. Is someone who's gonna reach out to Ash?
Yeah, I mean, I don't know her, but I can write to her.
Okay, no, I know her. I can certainly, I can reach out to her.
Okay,
So I'll just recycle my Katie email and reach out to, out to,
okay.
okay, Stephen, you're gonna talk to Tom? Okay, I see what we're doing here. Okay, great. I'll reach out to Ashley too.
Sorry. Is that okay? Like,
Mhm.
makes sense.
Um,
Sorry.
so we have 15 minutes. Can I like try to understand if we have like a plan? So from what
The
I
answer is no.
so that's I mean to plan to address. So the first thing I heard Namin mentioned several times is the differences across the literature, right? So I guess this is anyway will be step 0 for this project. Is it correct?
Yes,
Yeah, so maybe we can not today, but tomorrow, or we can start a table with the references. We already have several here, like parameters. I can volunteer for that, and people can modify. I can try to come up with something. And then the next step would be to do the second step, that would be more like actual work, is to run actually some codes, and to have some simple assumptions for the star formation, and for the galaxy we do some assumption on the mass, and we see what comes up. So that's like a big thing, and we break it down in several formation stages, right? At which we can compare the codes. So this is what I get from like overall.
yeah, there'll be some refinement that will have to go into that, right? It's not as clear cut as the literature. So,
Valeria, I started making a list of papers.
Okay.
I decided that there were enough people that could think of who could lead this, so I started looking at literature. I think people can, it's linked in the top. If you scroll up, there should now be a link from that.
This one.
And
okay,
from the discussion, it seems to me, as we are set on the background, then it's double wide words, and possibly we can look if IMCVN is affected, but we are starting from double wide words.
I think in the literature we should try to be more complete, because there is a few handfuls of papers specifically on LISA, on neutron star and black hole systems. I think we can easily include these.
Include Ilva's work on the STBs, your AIM-CVN paper, Kyle Krimer's AIM-CVN paper.
Yeah. So anyway, I started typing and looking a bit on ADS, but I may miss.
But now we can look at the Astro Working Group white paper.
Well, but it has 1,800 references, so there might
Good
be
luck.
more efficient way in finding the ones. But there might be in the sections, there may be a section that lists the relevant papers. But yeah, I would like to believe that I actually have read most of them.
I at least have most of them stored on my hard drive.
And I guess the coordinators will probably be willing to meet sometimes, and probably some other people might want to join sometimes. So that would be good too.
Yeah, once we have coordinators identified, we should
Mhm.
have a regular meetup to just kind of talk about and keep things moving, so.
Yep.
So we still have like 10 minutes before the break. Do you want to talk about how we're going to compute the background?
How what, Valeria?
Like how we are going to compute the foreground, background?
Ah.
Yeah, so from what I mean, I know at the end the fastest method is still using this SNR based iterative process, and there are, well, we have the code from Nikos that was updated to the code from Tyson, Neil, Cornish, and well, mainly from Tyson and Neil. And I think it was based on even earlier attempts to estimate the background. So that's sort of like a consolidated way of doing it. Do we want to reach out to Nikos, for instance, or to Tyson?
Yeah, I mean, part of, so whatever we do, we should all, I mean, we all probably have our own pipelines for doing varieties of this, but if we're going to do the comparison, we should agree on what we are going to do. And right now there's no standard public code that everyone uses. So in as much as that one's referred to a lot in the kind of Lisa data analysis community, that's plausibly a good one to start with. So if we reach out to them and we can get it operational for everyone, then it could become a very useful and standardized tool, particularly if we implement it for a big project like this. So I'm certainly in favor of going down that route.
Okay, I can actually ask, well, I can send an email to both Tyson and Nikos if they can maybe join us, hopefully tomorrow. And if not, I mean, they reply by email.
Okay. I think that's a great idea.
I may miss the start of tomorrow's discussion, but I'll try my best to be there or join a bit later.
We'll make sure to volunteer you for stuff.
I already started collecting the papers.
Oh, you did, right? Darn it. Heis is on it.
Okay, so we decide if we should take a break now, or do we have something else that we should discuss?
I think this all looks like good progress.
I'm surprised we have one volunteer, so it's already a win.
Silence makes wonders. If we don't talk, somebody will feel uncomfortable enough to volunteer.
Oh yeah, Astrid brought up a good point. It's actually, if you have somebody from the US and somebody from Australia and somebody from Europe, they will never be able to meet.
Yeah.
No, but it's possible to organize. Yeah, it's hard, but it's possible.
Yeah, that's actually a really good point. I mean, it's always hard if you have only 2 continents. That's already hard.
Mhm.
But like, yeah, that's
Let's keep that comment there.
actually a good point.
We could write a paper about the sociology of having coordinators over multiple continents. It'll be fun.
Well, one can do the following. So first, the person in the US works, then the person in Europe works, and then the person in Australia works. So, and you
Yeah,
have
but you have to
24-hour
talk-
day.
you
Yeah, and
have
send
to talk
messages
at
to the next person. Yeah,
Right, there's no way you talk unless
no real conversation. Yeah.
like doing it.
Well, what you do is you just have pairs of 2 meet. Like not all 3 ever meet at once, but pairs of 2 communicate. It's kind of like the LISA satellites, right?
Mhm, mhm.
Each of them is only linking to another pair.
That doesn't seem very efficient.
Coordinator exclusion principle.
Yeah.
Okay, we good?
Yes.
Okay,
Sounds good.
All
And then
right,
we
and
have,
enjoy your break.
Yeah.
and then, so the open discussion is just general science open discussion. It's not specifically about this project, right?
Yes.
Okay, rock and roll.
Yeah, the idea is that if people can bring new topics, or people who never speak can know their favorite topics
That we
that
should,
we should know of.
we should
Yeah.
make every student has to say something. Has to,
No, I was just making sure we didn't need someone to report on this discussion, so, yeah.
No, but it would be good to hear new stuff.
Yeah.
If possible.
Oh, so
If
what's the
not,
goal? It's just kind of exchange ideas, or is it even
Right.
starting new projects together, find collaborations, or is it really just whatever people?
It's
people-
freestyle.
Okay.
If somebody wants to find collaboration, I guess it's good to propose something. If somebody wants to discuss
Okay.
whatever observation or result is also good.
Okay.
There are no constraints.
Questions? Yeah, sounds good.
Okay. Rock and roll. See you all in a half
see you.
hour?
Yep.
Yep.
See
Okay.
you later.
See you later.
See you.
And we stay here, right? Good. This was very fruitful.